Okay, so now we're at Chapter 9B, Lesson 1, Part B, the second part. One of the more important parts of this particular lesson. What we're going to do here is raw construct in order to find a power series for a function. It is absolutely critical. I'm going to pull up the definition here, which at first you just got to take it in, accept it, and we can look at an anecdotal proof at another time. But a function, as long as it has derivatives of all orders, meaning it has the first derivative, second, third, fourth, nth, kth derivatives, as long as it has that, then a Taylor series is written as f of a plus f prime of a, and you can see it there or in the accompanying notes. What we're going to do is look at what's called a Maclaurin series, which is that Taylor series, except that it's centered at 0. So let's make some sense of this. So a Maclaurin series is a function f of x which is written as a sum of terms. Now, the first two terms, f of 0 plus f prime at 0, this will be centered at 0 times x. That's the linear approximation that you should be comfortable with. But we keep on going. We say f double prime at 0, x squared over 2 factorial, plus f triple prime of 0, x to the third over 3 factorial, plus dot dot dot, plus f nth prime at 0, x to the n over n factorial, plus dot dot dot. So this formula that you see here implies that it has a first, second, third, nth derivative at 0, and I want you to accept that this is true, that a function can be written like this. You need to accept that this is true for now so that we can construct some series, construct a series from a function. Okay, our first one here is f of x equals the sine of x, and we want to find a power series for that through raw construction. So raw construction means we actually have to find f of 0 because f of 0 is here. So f of 0 would be the sine of 0, and the sine of 0 is 0. Next, we take the first derivative at 0, which is going to be the cosine at 0, and that's going to equal, of course, 1. Moving along, we have the second derivative at 0, which is going to be negative sine at 0 is equal to 0. The third derivative at 0 is going to be negative cosine at 0, which is negative 1. And you can see the pattern if I took the fourth derivative, the fifth derivative, etc., etc., etc. I'm going to be able to plug each one of those into these coefficient values here. So this helps me to see that the sine of x is equal to, blows your mind, it is equal to 0, so I'm not going to write it, plus the next term, which is f prime of 0, this here, f prime of 0 times x, or simply 1 times x. Then the next term, because f double prime of 0, 0 is not there. The term after that is going to be minus x to the third over 3 factorial. Can you see what the next one is going to be? It's going to be an odd derivative, and it's going to be positive. It brings us back up to here. So it's going to be plus x to the fifth over 5 factorial. The next one, can you guess it? Minus x to the seventh over 7 factorial. And this continues on and on and on. It's a little bit of a skill to determine what the nth term is. If you want to try to figure it out yourself, pause it, because I'm going to give it away. We see that this strictly alternates, and then x is raised to an odd power, so 2n plus 1, and that's going to be over 2n plus 1 factorial. And So this here is an equal statement. The sign of x is actually equal to the sum that you see here, this infinite series. Now, of course, it's not going to be necessarily true for all x, and so we would have to do some kind of test to determine the interval of convergence. Can you guess what we could do to the nth term to find the interval of convergence? If you are thinking Hart ratio test, then you are absolutely correct from 9a, lesson 9a, and you will find that the interval of convergence is x is an element of reals, or in other words, this will converge for all values of x. Okay, so we're going to take a look at number 2. G of x equals e to the x, and we are going to raw construct to find a power series. So we're going to need g at 0, which is simply e to the 0, which equals 1. We're going to need the derivative at 0, and the derivative of e to the x is itself e to the x, so e to the 0 is 1. The second derivative at 0, behold, is also 1. So you'll see no matter how many derivatives I take, it's always going to be 1. That is, the derivative is always going to be 1 at 0, the first, the second, the third, so on and so forth. So if we're going to fit this into that format, well, g of 0 is 1 plus 1 times x plus 1 times x squared over 2 factorial. All the coefficients are 1. I'm not writing the number 1, but I'm saying the number 1. Times 1 times x to the power of 3 over 3 factorial plus dot dot dot. Plus, the nth term here is fairly easy. It is not alternating at all. It's x to the n over n factorial plus dot dot dot. I mean, this is so cool. Again, you can't, I'm not showing you, but I am now. 1, 1, 1, 1. Where do these come from? Right here. These are the coefficients for every derivative at 0 is equal to 1. Now we also, like any other problem, we want to discuss the interval of convergence, and you would do the interval of convergence ratio test on the nth term, and again, behold, the interval of convergence, x is an element of the reals. So that's really cool. No matter what value of x you would plug in, this infinite series would equal e to that value of x. Okay, the final example for raw construction, example number 3, we are going to resort back to f of x, and this is going to be 1 over 1 minus x. If you look at this, I want you to say, wait a minute, didn't we in part A already come up with a power series? We did. We used the fact that this is a sum of a geometric. However, we can always raw construct. I don't advise always raw constructing, but you can. So let's do it here. F of 0 is equal to 1 over 1 minus 0, which is equal to 1. Now we need the first derivative at 0. Okay, let's think about the first derivative. Let's call this x. All right, so we'll get the function and then we'll plug in 0. So the derivative of this, treat this like 1 minus x to the negative 1 power. So we have negative 1 minus x to the negative 2 power times negative 1 via the chain rule. And so then f prime at 0 is going to equal positive 1. Let's take a look at the second derivative of x. And the second derivative of x then would be -2, 1 minus x to the -3 power, and again times -1. And f double prime at 0 then would equal 2. I don't know if you see a pattern. Let's take a look at f triple prime of x, which is going to be -6, 1 minus x to the -4 power times -1 chain rule. F triple prime at 0 then comes out to be 6. It goes 1, 2, 6. I don't know if you can guess what the next one's going to be, but the fourth derivative at 0 comes out to be 24. Okay, so now our function, our function is going to be these coefficients in front of that general x plus x squared over 2 factorial, etc., etc. So our first term is 1 plus 1 times x plus 2 times x squared over 2 factorial plus 6 x to the third over 3 factorial. The factorials and the power are fixed. It's just these coefficients that are unique to the problem. Plus 24 x to the fourth over 4 factorial plus ... Now, before I write the nth term, you see something beautiful in this. That cancels out, that cancels out, and that cancels out. And that will continue. So we have 1 plus x squared plus ... plus x to the power of n plus ... which is exactly what we found when we thought of it as the sum of a geometric. And this is great. Because we did raw construction and we're not treating it as geometric, we can use the ratio test, but we are going to find the same interval of convergence that we found before, which is between -1 and 1, not inclusive. So this is pretty awesome. The main thing now that you have to accept, and we will talk about this at another time, is that, again, f of x, when centered at 0, my friends, is equal to f of 0 plus f prime at 0x plus f double prime of 0 x squared over 2 factorial plus ... plus the nth derivative at 0 x to the power of n over n factorial plus ... If you can accept that for now, through an investigation, you'll accept it better. But if you can accept that, then you can raw construct a whole host of power series. One final note, please don't overuse raw construction. There'll be other ways, better ways, but this is a way that you must know. That's going to be the end of part B, and it'll probably take about 4 parts to finish this lesson. The end.